So this topic is going to be the component method of vector addition. So you'll remember from last year that when we take two vector values and add them together, we add them tip to tail. And if we're subtracting vectors, we add the opposite vector. All right. So vectors add tip to tail. And we did some stuff with some examples last year. So we'll start off with a little bit of a review. Okay, so an example. Bob walks 10 kilometers north, then 15 kilometers east. This takes him 5 hours. Calculate Bob's velocity for the trip. All right, so we're going to recall, first of all, that to be a vector value, you include both the direction and the magnitude, and that you can represent them using numerals, but in this case, you have to actually graphically represent this situation, okay? So we're going to draw vector arrows to represent his travel north. Let's actually use an arrow. Okay, so he starts at home and goes 10 kilometers north, followed by 15 kilometers to the east. So in order to get his velocity, what we actually need is Bob's displacement. Okay, and his displacement is always measured from his starting point to his finishing point. So that would be represented by a vector arrow pointing up over here. Start to finish. So it's somewhere in the northeasterly direction, but we have to be more specific than that. We're actually going to have to indicate this with an angle, okay? So the first thing we'll do is we'll calculate and we'll figure out the actual magnitude of the displacement, and we'll use Pythagorean theorem to do that. So it works out to roughly 18 kilometers. All right. So far so good. Now what we need to do, though, is we need to figure out at what angle, or what heading, if you want, Bob's going to go at. All right, so we're given the opposite, and we're given the adjacent sides of this triangle to work with. So theta then is going to be equal to the inverted tan of your opposite divided by your adjacent. If you're not sure how I did that, I'll show you in just a second. I know sometimes people forget trig after a break. So that should give you 56 degrees and change to the east of north. So we're going to write that as east of north. Okay, so a little note on using 56 here. There's a rule of thumb that basically says to use the smaller of the two possible angles as measured from the cardinal directions. So that seems like complicated, but basically all it means is if this angle ends up being larger than 45 degrees, we'll use its complementary angle instead and measure north of east rather than east of north. So if this is 56 degrees, this should be 34 degrees. So the preferred way to write it would be 34 degrees north of east, because we want to measure from the closest cardinal direction. That's just a rule of thumb. It's not saying 56 is necessarily wrong, but the preferred way is to write it like this. Okay, now we're almost finished. We just need to do our velocity equation here. So displacement divided by the time it took. So we had 18 kilometers. And I think I said it took 5 hours. Gives me 3.6 kilometers per hour. And then we're going to tack on the direction, 34 degrees north of east. So that's review from what you learned last year. So this is fairly easy because it's two vectors that are at right angles to each other. But oftentimes you'll run into scenarios where they are not at right angles to each other. So we're going to use this general idea, or this general, you might want to call it an algorithm, I guess, to solve problems like this for any angles and really any number of vectors. You could add 5 or 6 or 7 vectors together and this will still work. Okay? So that's where the component method comes in. So let's start with an example, and we'll still do a displacement scenario. So find the displacement of an aardvark that walks 10 kilometers northeast, followed by 10 kilometers 20 degrees south of east. So there's a picture of an aardvark, which I think looks like a cross between a pig and a rabbit. And what we're going to do is we're going to draw a bit of a Cartesian plane here to try to map what this creature is doing. So we're going to look at it like this. There is north, there is east. If we say something walks to the northeast, it just means it's walking exactly halfway between here, or 45 degrees north of east. Okay, so for 10 kilometers, it walks like that. And it walks another 10 kilometers, but we're now 20 degrees to the south of east. Like that. Okay, so what we're after then, once we've added these vectors tip to tail, is this right here. Here's your start, here's your finish, okay? Here's your displacement here with the dotted line. All right, so essentially, the component method is going to look at each of these vectors separately. We'll call this vector A. We know that's 10 kilometers. And vector B, we know that's 10 kilometers. So our goal here is to do this. It's to map out our motion in the x direction. And in this case, what we'll be doing is we will figure out how far vector A moves the aardvark on the x-plane. Oh, no. Okay, hang on a sec here. Back to there. Make this a nice, easy to see color. And make it an arrow. Okay. So how far the aardvark moves vector A. And we're going to call that something. We're actually going to label that A sub x. So how far A moves it in the x direction. Okay. So it's like we're walking along beside the aardvark, but we're constrained to only moving in the x direction. Okay. And then there's also going to be, why is it automatically a dotted line? I don't get it. A y component. A y component of the, oh, for goodness sake, I'm struggling here. Okay. A y component of A. So AY. how far the aardvark moves in the y. All right, so it's like, you know, if you were to say, like, define this point on a Cartesian plane, it would have an x coordinate and a y coordinate. So that's what we're looking for. What is its x coordinate? What is its y coordinate? Does that make sense? Okay, and then we're going to look at the second vector, and we're going to see that b, vector b, moves the aardvark further along in the x plane. We're going to define that as bx, and it also moves it in the y plane. So back against the grain down to about there. And that's your by. Once we're done that, we'll see that, and I'm going to draw all over here, but you can get rid of it after. We'll see that once we have those values, they're going to end up showing us exactly where that creature is. Okay, so its x component, or its sum of its x components and the sum of its y components will give you its new point on the plane, right? Its new x and y. So we're going to solve this kind of like longhand. There are much shorter ways of doing this, especially as you get better and better. You can actually work these problems just right in line with what you've drawn here. I would always suggest, though, like draw out something graphical for you to kind of follow along with. It helps you to check if your answer makes sense. So we're going to tackle the vector A first. We're going to find its components. So let's quickly draw it here. And you can just sketch one of these out right on your piece of paper. It's not like it's a scale drawing or anything. It just has to be close to what real life would be like. Oops. Ah! Aardvark attack. Okay, 45 degrees. So here's the AX, and here's the AY. This is 10 kilometers. We could also draw the AY over here, and we're going to define that based on its relationship to the angle we're after. So this is the adjacent angle. So we're going to be able to solve for that as 10, that's the hypotenuse, kilometers, times the cosine, 45 degrees, and AY, which is 10 kilometers, times the cosine of 45 degrees. And you'll find that those values both equal the same. So we get about 7.1 kilometers, and we're going to say that's towards the east. And we're going to get 7.1 kilometers towards the north. So we can actually just add that in right here. 7.1 and 7.1. So north and east. Okay, so we'll make more space for ourselves. We'll just put that over there. And then we'll tackle vector B. So draw yourself a new little set of guidelines here. Fill in what you know. That's 20 degrees. Okay. This was 10 kilometers. So we got BX there. And BY there. So BX, well, that's the adjacent angle. Okay, so how far do we go in the X direction? BY is 10 kilometers times the sine, 20 degrees. Just realized I wrote cos in here twice. That one should have been sine. It didn't matter because of the angle, but it would have mattered if it was anything else but 45 degrees. So that should have been sine. It's just a typo on my part. So solving for these, BX, you get another 9.4 kilometers to the east. Okay, and BY gives you 3.4 kilometers to the south. So I'll just move that out of the way too, shrink it down. Okay, so I don't really like working right on here. So what we're going to do is this. We're going to go X net. So the net in the X direction. So X net is 7.1 kilometers east plus 9.4 kilometers east. So that should give us 16.5 kilometers in the easterly direction. So the sum of these two values gets you to here, 16.5 km. Okay. Y net, a little more tricky, because you have 7.1 kilometers. That's to the north. Plus 3.4, but it's in the opposite direction, so we need to bring in that negative sign to represent that it's traveling to the south. And you get 3.7 kilometers left, right, in the north direction. So now what we need to do is we need to take this information and we need to construct a new right angle triangle from it. So we want to get down to a right angle triangle in the end. So we know then that it goes a total distance of 16.5 to the east, followed by a total of 3.7 to the north. And now this is just like a problem that we've learned in the past because you've created a right angle triangle. And that's always going to be the goal. And we will quickly solve for this. And that's sort of that for this topic. Something that's interesting and a question that just got asked here. Let's just change this hypotenuse so we know that it is the final sum of all our vectors. But a question was, why did I go to the east first, or why did I draw the easterly vector first? Well, it turns out it doesn't really matter which one you put first, right? I could have drawn this first, followed by this one. As long as they're tip to tail and I've done it correctly, you'll see that the value I get is going to be the same either way. The reason I chose to do it this way, though, is because if I'm finding the angle, I don't have to do the extra step, right? If I go this way, I'm going to get a much larger angle than 45. So I mean, it basically just saves me a step. I don't have to convert after. Let's get rid of that. Okay, so first we need to find the magnitude here. So the magnitude of the displacement is using the Pythagorean theorem. We have that. And then we need to find the value for the angle so we can get our direction. So opposite over adjacent. And let's solve it. Okay, so we just collect the solutions to these, and you get that the displacement of the aardvark is 16.9 kilometers, 12.6 degrees to the north from east.